Okay, so for the last step of this problem, we're going to go through and find the matrix exponential given the 3 p's and the 3 r's that we found earlier in the problem-solving process. So our e to the at is going to have our e to the negative t times 1, 0, 0, 0, 1, 0, 0, 0, 1 plus a t e to the negative t times the matrix 0, 0, 0, negative 1, 2, negative 1, negative 2, 4, negative 2, and then a 1/2 t squared times the 0 matrix. All right, now we're going to go through and distribute all of this in combined like terms and put it into a single matrix. So from the first one, we're going to pick up an e to the negative t and no other entries. And then in the next entry in the top row, it's going to be all zeros. And then we're going to have our third one being all zeros as well. For the next one, we pick up a 0. Then we pick up a 2, t, e to the negative t, and then nothing else. And then for the middle, we pick up 2 terms. That's an e to the negative t plus a 2t e to the negative t. And then the last term is going to be a negative t e to the negative t. And then down here, we're going to have a 0 from the first, a negative 2 t e to the negative t. And then we're going to have in the middle a 4 t e to the negative t. And then, of course, we pick up nothing from the last one. And then we're going to have, for the last entry, an e to the negative t minus 2 t e to the negative t. And that right there is our matrix exponential. The next thing we can do is now go in and write down our solution for our 3x3 system. So that's why if t is c1 times the first vector plus a constant c2 times the second vector and now because it's 3x3, a third constant c3 times the last vector of 0, negative t e to the negative t, and e to the negative t minus 2t e to the negative t. And we could go ahead and actually verify this solution by substituting into the original differential equation. And you could also verify linear independence by going through and calculating that 3x3 determinant and showing that it is not equal to 0.